Welcome to next class in time independent perturbation theory. Today we will discuss another application of time independent perturbation theory. It is called the Zeeman effect. Zeeman effect is the splitting of energy levels of an atom when it is placed in a magnetic field. When an atom is placed in a magnetic field, the electron in the atom will interact with the magnetic field, thereby splitting the degenerate energy levels. This splitting of energy levels is called the Zeeman effect. It may be also called as the shifting of energy levels, because if the energy levels are shifted, then the energy spectra are split into different parts. Now, for a single electron, as in the case of hydrogen atom, the interaction energy of the spin and orbital dipoles with the external magnetic field can be given by Hz is equal to minus mu dot B, where mu is the magnetic dipole moment and B external is the external magnetic field. Now, in the case of an electron, it has two types of magnetic dipole moment. One is the spin magnetic dipole moment. It can be called as mu S, which is equal to minus E by M into S, where S is the spin angular momentum. And the orbital magnetic dipole moment, which is called as mu L, which is equal to minus E by 2M into L, where capital L is the orbital angular momentum. Therefore, the energy contribution due to the interaction between the spin and orbital magnetic dipole moment and the external magnetic field will be E by 2M into L plus 2S dot B external, if this mu E and mu L are mu S and mu L are provided in this expression, we get this one. So, the energy will be the average value of this one. We have to find the expectation value of this one. Now, the nature of Zeeman splitting depends on the relative values of the external field and internal field. The external field is represented by B external, and there is an internal field. The internal field means, which we have already discussed in the last class, that the spin and orbital motion of the electron interfere each other, producing a spin-orbit coupling. The spin-orbit coupling is an internal Zeeman effect actually. It is also an interaction between the spin magnetic dipole moment of the electron and the orbital motion. So, it is called the internal Zeeman effect. We can call it as the spin-orbit coupling is also called as internal Zeeman effect. So, actually there are two magnetic fields, the externally applied B external and the internally present B internal. So, the strength of the nature of Zeeman splitting depends on the relative values of these two fields. If the external field is much less than the internal field, then we can take the Zeeman effect as a perturbation to the existing hydrogen atom. Existing means the hydrogen atom with spin-orbit coupling. So, in that case, the Hamiltonian of the hydrogen atom includes the main Hamiltonian of original hydrogen atom plus the relativistic correction plus the spin-orbit coupling term. So that is now it becomes the main Hamiltonian, or the spin-orbit coupling becomes part of the main Hamiltonian, and the additional Hamiltonian, that is Hz dash, that is called the Zeeman Hamiltonian or Zeeman component. The Zeeman effect becomes a small perturbation. So this is called a weak field Zeeman effect. Now, if the externally applied magnetic field is much stronger than the internal magnetic field, then in that case Zeeman effect dominates. So Zeeman effect comes in the main Hamiltonian part, and the fine structure, that is the spin-orbit coupling and the relativistic correction, there becomes the perturbation part. So this is called a strong field Zeeman effect. And in the intermediate zone, in which B external and B internal are comparable, then it is called a medium field Zeeman effect, and that treatment is somewhat very difficult. The strong field and weak field are easy to calculate. So we will calculate each Zeeman effect one by one. So the first one is weak field Zeeman effect. In this case, the external magnetic field is much less than internal magnetic field. So here the Zeeman contribution is E by 2m into L plus 2s dot B external. It becomes the perturbation to the main Hamiltonian. Now remember, the main Hamiltonian includes the original Hamiltonian of hydrogen atom, which was studied in the theory of hydrogen atom. Then the relativistic correction, then the spin orbit coupling. Here the relativistic and spin orbit coupling are on the same comparable value. So these three Hamiltonian now forms the main Hamiltonian. Our new Hamiltonian, that is called the contribution from the Zeeman effect, it becomes a perturbation to this main Hamiltonian. Now, as usual, to apply the perturbation theory, first we have to select a good basis of unperturbed states. Good basis means a basis in which our perturbation is diagonal. If the perturbation is diagonal in the basis, we can proceed with the non-degenerate perturbation theory. Now here, because of the presence of this spin orbit coupling, the original eigenstates of the hydrogen atom, that is psi NL, NL, ML, MS, these eigenstates are no longer good because these eigenstates psi NLM are not eigenstates of H dash of SO, because this H dash of SO or spin orbit coupling will not commute with the LZ or SZ. Therefore, these are not good. If we take these states for the treatment of perturbation theory, then we will have to proceed through the degenerate perturbation theory, and we will take a matrix and it has to be diagonalized first. So it becomes very complex. So we will take another basis vector. Here the spin orbit coupling, as usual, as in the last class we have discussed that the total quantum number states, that is the eigenstates of L square, S square, J, that is total angular momentum, and Jz, that is called the NL, J, Mj. These eigenstates are also eigenstates of this H dash of S, or that is the spin orbit interaction term. It commutes with these operators L square, S square, J square, and Jz. So this forms a good basis for using in perturbation theory. And also here our perturbation is Hz dash. It is equal to E by 2m into L plus 2s dot B external. Now we can see that on an average this vector, that is L plus 2s, also commutes with this L square, S square, J square, and Jz. So the perturbation Hz, that is the Zeeman perturbation, is also diagonal in the representation or in the basis NL, J, Mj. So we can use the non-degenerate perturbation theory, which is the basis formed by NL, J, Mj. So here the perturbation Hz is, so here the Zeeman perturbation is a small perturbation which is piled over another larger perturbation H dash of SO and H dash of R, that is called the relativistic and spin orbit coupling. So we can take the relativistic and spin orbit term as part of the main Hamiltonian, and this Hz dash is taken as the perturbation. So this perturbation will lift the remaining degeneracy, because we have seen that even in the fine structure, the energy levels of hydrogen atom is represented by E and J. So it has the same value for a given value of J. For a given N and J values, the energy levels are same. So there is some degeneracy still remaining in the J value. So that remaining degeneracy will be lifted by using the Zeeman effect. So by the first order perturbation theory, the correction to the nth energy level is the expectation value of this Zeeman term on the basis NLJMJ. So Ez of 1, that is the first order correction due to the Zeeman effect, which is equal to expectation value of Hz, that is equal to NLJMJ, Hz, NLJMJ. Now Hz is equal to E by 2m into L plus 2s into B external, dot B external. Now we have seen that, we can see that this Lz is an eigenstate, the NLJMJ is an eigenstate of Lz, but NLJMJ is not an eigenstate of SZ. So finding the average value of S is somewhat difficult, so we will proceed it in an indirect way. For that, we have seen that we can see that L plus 2S is equal to L plus S plus S, where L plus S is equal to J, that is total angular momentum. So this can be written as J plus S. Therefore, our correction to the energy becomes E by 2m can be taken out, and B external is also the externally applied magnetic field, so it can be taken out because it is not depending on the state of the hydrogen atom. So B external dot, there is a dot is here, then the remaining will be NLJMJ into J plus S, that is the expectation value of J plus S. Now the states NLJMJ are eigenstates of Jz but are not of Sz. So to find the average value of S, we proceed in another way. We can see that the spin angular momentum S precesses about the total angular momentum J. So the average value of S is the component of S over J. That is, we can see here, this is the diagram. The total angular momentum is there. The orbital angular momentum L and the spin angular momentum S are precessing about that total angular momentum. So as S precesses about the total angular momentum, we can have the average value of S will be the projection or the component of S along J. If theta is the angle between S and J, then the projection of S will be S cos theta. Therefore, average value is equal to S cos theta. Average value is equal to this one because the component perpendicular to J, that is in this direction and in this direction, they are equally distributed in all directions in a plane perpendicular to the total angular momentum. So they will cancel, because if there is one component in this direction, another component is there in the opposite direction. So there is only this component along J is the non-zero term. So we can see that average value of S is equal to S cos theta along J cap. It is a vector quantity. So that S cos theta can be written as S dot J by J, because S dot J is equal to S into J into cos theta by J, and unit vector J can be written as vector J by J, so it becomes J square. Now L is equal to J minus S. Now we have to find the value of S dot J. For that we take LD is equal to J minus S. Therefore L square is equal to J minus S dot J minus S, or L square is equal to J square. Now they are scalar quantities, J square plus S square minus 2S dot J. Scalar means they are operators actually. The dot product is taken here. So minus 2 into S dot J. Therefore we have S dot J. Therefore S dot J is equal to J square plus S square minus L square by 2. Or it is equal to, if we take the expectation value of this S dot J, we take 1 by 2 H cross J square. Expectation value of J square will be J into J plus 1 H cross square. Here S into S plus 1 into H cross square minus L into L plus 1 into H cross square. So H cross square is taken out. Therefore, we get the expectation value of J plus S. That is, we have to find the expectation value of J plus S. This is the expectation value of J plus S. So we get the expectation value of J plus S is equal to expectation value of J plus S is equal to Sj by J square J. So if we take J outside, we get expectation value of 1 plus S dot J by J square into J. That is equal to 1 plus S dot J by J square is S dot J is this one, and the expectation value of J square will be J into J plus 1 H cross square. So this H cross square and here the H cross square cancels. The remaining will be J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2. That is this 2 into this J square. Expectation value of J square is J into J plus 1, and H cross square and H cross square gets cancelled. And there will be expectation value of J, because this is outside, it is here also again. Therefore the energy correction becomes E by 2m B external dot this term, that is the 1 plus J into J plus 1 S into S plus 1 minus L into L plus 1 by 2 in J into J plus 1 into the expectation value of the total angular momentum. Now we have to take the dot product between B external and the total angular momentum J. For that, the magnetic field, as usual, it will be acting along the Z axis. Therefore, B external dot J will be equal to B external into jz, because dot j becomes jz, or j cos theta, it becomes jz, and the average value of jz will be mj into h cross with respect to the eigenstates in nlj mj. The average value will be mj into h cross into b external. Therefore, the first order correction to the Zeeman due to the weak field Zeeman effect, it is 1 plus j into j plus 1, that is this time into h cross by 2m into mj into b external. Now the quantity inside the brackets, this quantity is called the lambda g factor and is represented by gj. Also h cross by 2m is the famous mu b, that is the Bohr magneton. So the Zeeman energy or the correction to the energy levels due to the Zeeman effect, weak field Zeeman effect, Ez1 is equal to Gj mu b mj b external, where mj is the component, z component, the angular momentum along with the z component of the quantum number along with the z component of the total angular momentum vector, that is mj. So the total energy is the sum of the fine structure energy Enj that we have already discussed. Now it is the unperturbed energy levels. Into that energy level we are adding a correction due to the perturbation. So that unperturbed energy level is the fine structure energy and the Zeeman energy, it becomes the total energy, that is Enj into Ez of 1. Therefore, E is equal to Enj plus Ez of 1, that is equal to En into 1 plus, that is the Zeeman, that is that as we have derived this expression in the last class for the total fine structure energy of the hydrogen atom. So that is equal to En into 1 plus alpha square by n square n by j plus half minus 3 by 4 plus the energy correction due to the Zeeman effect. Now the implication of this result is, we have seen that in the fine structure for a given j the energy is same, because and we have seen that, for example, 2s half and 2p half, they are different states but they will have same energy even in the fine structure because they have same j value. This half represents the j value. So 2s half, 2p half will have the same energy. They are still degenerate even in the fine structure. But when the Zeeman effect is considered, for a given j, the quantum number mj can have values from minus j to plus j, or it can take 2j plus 1 values. So each level with quantum number j, that is the total angular momentum quantum number j, will split into 2j plus 1 levels. For example, this 1s half, it has j is equal to half, so it will split into 2j plus 1, that is 2 into 1 by 2 plus 1, that is into 2 levels. Similarly, this 2s half will split into 2 levels and 2p half will split into 2 levels. So this level, these 2 levels which were originally degenerate, now it becomes non-degenerate. They are splitting into 4 levels, and the 2p 3 by 2 level will split into 4 levels because it is 3 by 2. So 3 by 2 into 2 plus 1, it will split into 4 levels. So, and also we can see that for a given j, the spacing between the energy levels are equal. Here the spacings are equal. Here also the spacings are equal. But this spacing and these spacings are not equal because that will depend on L value also, because they have are having different L values. And also, so the Zeeman effect splits the degenerate states Enj into equally spaced 2j plus 1 states of interstate spacing. So the Zeeman effect splits the remaining degeneracy. An example is the ground state of hydrogen atom. For that, n equal to 1, L equal to 0. So s is equal to 0. So j can have only half. J is equal to s. L plus s now is equal to half. Mj can have two values. Mj is equal to plus or minus half. Mj can take values from minus j to plus j. So minus half and plus half. So we can calculate Gj is equal to, it will be 2. The energy levels are En into 1 plus alpha square by n square into 1 plus j plus half here j is half and another half minus 3 by 4 into 2 mu b into mj into b external. So it becomes En into 1 plus alpha square by 4 into this 2mj becomes plus or minus 1, that is plus or minus mu b into b external. So the energy level Enj, that is 1 half split into 2 levels, that splitting is shown in this diagram. Here minus 13.6 is En. So minus 13.6 into 1 plus alpha square by 4 electron volt, that represents this term. It is the fine structure of hydrogen atom. Along with that, we have two components that split into two components. If we are plotting the splitting with respect to the variation of mu b b external, mu b b external is taken along the x-axis and along the y-axis energy is shown. So for mj is equal to plus half, we will get one state, and for mj is equal to minus half, we will get another state, such that the energy difference between these two states are 2 into mu b into b external, because mu b into 1 becomes plus mu b into b external and the second becomes minus mu b into b external. So the total difference will be 2 into mu b into b external. So the important point is the Zeeman effect lifts the remaining degeneracy in the fine structure of hydrogen atom. So please try to answer what is Zeeman effect, what are the three different regions of Zeeman effect, and explain the weak field Zeeman effect.